Next, we will import data exported from an asset management tool to populate server farm and storage rows. We will then run a CFD simulation. If we look at the equipment overheat plot, we see that all cabinets achieve the required safety margin of 5 degrees C for this data hall, except cabinet AA14. If we look more closely at the cabinet, we can see that one piece of IT equipment is predicted to overheat, and 4 more do not achieve the required safety margin. We can create a summary for the room using View, Add View, Room Summary. This shows information about the room in a tabular form. The Equipment Temperatures section of the Room Summary confirms that the equipment in slot 29 of cabinet AA14 is predicted to overheat by 0.5 degrees C. The traditional approach to these hotspots and overheat is to turn down the ACU set points. Let's do so in the software to check whether it will work. In theory, reducing the set points by 1 degree C should stop the overheat. This can also be seen easily from the room summary. Note, however, that a 1 degree reduction won't achieve our 5 degrees safety margin. If we look at standard recommendations from the American Society of Heating, Refrigerating and Air Conditioning Engineers, or ASHRAE, they also suggest that we should be dropping our set points by about 5 degrees. However, just for the sake of this demonstration, let us mimic what happens in real life in many data centers. The set points are reduced by the minimum amount, and the data center is just on the verge of overheating. Having solved the model with the new set points, we can see from the overheat plot and room summary that the traditional method of reducing the set points has improved the room and eliminated the overheat, but we have no safety margin. Is there a better way to avoid overheating and regain the 5 degree safety margin? Let's use Six Sigma FM to diagnose why the equipment is overheating. We can see that the temperature in the cold aisle in front of the overheating cabinet is around 18 degrees C, which is acceptable. This means the overheat must be an internal cabinet problem and not a room-level problem. By adding streamlines to the inflow of the overheating equipment, we can see that air is recirculating within the cabinet. The hot equipment exhaust is being taken straight back into the inflow rather than exiting the cabinet and returning to an ACU. We can improve this by adding blanking plates. First, we must schedule a new change. The software can automatically add blanking plates to the cabinets you choose. Looking at the same cabinet, we now see that the equipment at the top gets its air from the floor grill and the recirculation has been eliminated. We can see from the overheat plot that installing the blanking plates is a much better solution than turning down the set points. It's completely eliminated the overheating and has given us a safety margin. In fact, if we look at the room summary, the blanking plate installation means we are now overcooling the data hall with almost a 7-degree safety margin. We should be turning the ACU set point up to stop overcooling and save energy. We have two choices. We can turn up the set points by 7 degrees, or we can turn them up by 2 degrees and maintain a 5-degree safety margin. We will choose the second option. After resolving the case, we can see from the overheat plot that the equipment is still cooled effectively, even at these higher ACU return temperatures. Increasing the ACU set points will result in an energy saving and in turn a saving on cost. It's important to remember that we've maintained a safety margin of 5 degrees. There's the potential of creating even greater savings by reducing this margin. We've seen how Six Sigma FM can interact with asset management tools, but it also comes with a deployment tool of its own, Six Sigma ITM. Six Sigma ITM is an easy-to-use wizard that gives IT professionals access to the benefits of the virtual facility. The focus of Six Sigma ITM is the smart deployment of IT equipment in data centers. It makes use of the airflow and thermal analysis performed in the virtual facility to inform IT deployment and reduce the risk of thermally induced failure. Six Sigma ITM communicates with Six Sigma FM to keep the virtual facility up to date with IT plans and to give the facility manager the chance to simulate IT plans before deployment. Let's look at Six Sigma ITM and see a few examples of how it can be used. We will install new equipment. There are some simple views available, each one providing different information about the cabinets in the facility. For example, you can see the amount of available space in each cabinet, available cooling, and other useful data. We need to specify a project name and date in order to track our progress. We can choose items to be installed from the list of equipment available in the storeroom. Once we've done this, we are provided with a view which shows us in green which cabinets have the cooling capacity and the space to house the new items. You can see here cabinet 16 does not have the cooling available for our chosen equipment. We will install equipment in cabinets 17 and 18. The new items are highlighted in blue in a cabinet view. We can now see a summary of the reservations made in cabinets for our 3 chosen items, as well as the planned dates of installation. We will now return to Six Sigma FM to see the changes that have been made. The reservations and installations planned in ITM have been added into the Six Sigma FM timeline for the facility manager to analyse. There is the option to reschedule the events if necessary. Otherwise, it is easy to accept or reject the changes. If we accept, the new equipment is shown in the virtual facility.